So, whenever we talk about functions, we usually mean that the function is defined for a real variable, that means one single variable, that is like f x. So, x is a real variable, and with respect to this kind of function we have defined or we have studied different concepts or different properties like limit or continuity, that means whether a function is continuous at a point or whether a function is differentiable, like this. Now, the question is it possible, having defined all these concepts and also we know few results on this, is it possible to extend this basic concept of function when there is more than one variables? Like suppose you have say two variables x and y. So, the first question is, can we define a function based on these two variables? The answer is obviously yes. Next question will naturally come, okay, can we extend this to more than two variables? Like if we have x1, x2, xn say variables, can we define, or rather which is a vector of dimension n, that means having n components, can we define a function on that? More importantly, can we go one step ahead, like can we define a vector of functions where each function is a function of several variables? So, today we are going to discuss such type of extension, such type of functions which are vector valued or defined on vector observations, and we will also discuss limit or continuity with respect to that function as well as differentiability. So, today we are not going to discuss everything in great detail, or we are not going to concentrate on several theorems, but rather we focus on the basic concept of these functions and how to define limit or continuity or differentiability of these functions. So, the main objectives of today's talk on functions of several variables, or rather preliminaries, are like this. So, we will first define a function and then the limit of a function of several variables. We will also define continuity, its definition, and we will discuss some features of this property, like whether a function is continuous or not, using some examples. And then we will define the condition of differentiation, and at the end we will discuss Taylor's formula, Taylor's theorem, which we know for the function of a single variable. But first let us consider a few notation. We know usually we denote a single variable which is of dimension 1 by x. So, if nothing is written, if x is written, we usually consider this x to be a single variable. Now, if we want to extend this single variable to a number of variables, we can think of bold x, which is x1, x2, xn prime. That means we consider this as a vector of n variables at dimension n. Now, throughout this talk we will consider this bold x as a column vector having n components. So, if we write it as a row vector, we should put one prime at the end, like x1, x2, xn whole prime. So, this is a row vector. So, that means x is a column vector. Now, we define a function which is a scalar function of more than one variables, in this case n variables. That means it is based on a vector valued variables. So, x1, x2, xn, but f is a scalar. But we can extend this immediately to define a vector of k such functions. That means in this case f x equals to f1 x, f2 x and f k x, where each f1, f2, f k is a function of function of n variables, that is x1, x2, xn, or a vector valued function x of dimension n. Now, if we put here instead of k, if we put m or r, then it would be a vector of m or r functions. That means f itself has a dimension of k or m or r, whatever, but it is expected that it is greater than or equals to 1. So, suppose first consider that f is a function S to Rm, where S is a subset of Rn, that means n dimensional space. Now, for any point A belongs to Rn, that means A itself is an n by 1 vector, and B belongs to Rm, that means B is a m by 1 vector, we write limit as x goes to A, f x equals to B, or we can say that f x tends to B, or f x approaches to B as x approaches to A. This means, what we mean is this, that means distance or norm of fx minus b, that means the difference between fx minus b in the sense of a particular norm which is defined on the space where fx is defined, this norm goes to 0 as x goes to a, or norm of x minus a goes to 0. So this means that distance between fx and b, distance is measured in terms of norm or a metric which is defined on these appropriate spaces, appropriate metric. This goes to 0 as norm between x minus a, or norm of x minus a goes to 0. So this is a concept of limit, just the extension of the limit of a single variable function which we already know previously. Now note that like the concept of single variable case, that it is not required that f to be defined at the point a itself. It is not necessary. It would be good if it is defined, but it doesn't really, it is not a necessary condition. Now once we see that this limit can be defined analogously that what we have defined in case of single variable function, we can think of continuity, and it is easy to extend this notion like a function f is said to be continuous at a if f is defined at a, and if limit of fx equals to f of a as x goes to a. That means f is defined at a and the limit should be equal to f a, then only we can say f is continuous at a. And we say that the function f is continuous on a set S if f is continuous at each point of S. This is very important. Let us consider one theorem which is again following from the theorem of, or some properties of continuous functions on the single variable on the real line. So theorem is that suppose limit x goes to a fx equals to b and limit gx x tends to a equals to c. That means we have two vector valued functions defined on a vector of variables or vector valued variables or a vector, and the limit exists as x goes to a. Then it is easy to show that limit x tends to a of fx plus gx is nothing but the sum of the two limits, that is b plus c, and at the same time limit x goes to a lambda into fx would be equals to lambda times the limit of fx as x goes to a, that is lambda times b for every scalar lambda, and similarly limit of product of two functions equals to product of the limits. And also this is very interesting that limit of norm of fx as x goes to a equals to norm of the limit. This is very important, and this has immense application in many theorems or in studying these functions of several variables. So we see that we can propose a few results that are analogous to the function of real variables, single variable rather. Let us consider a few examples. First, consider fxy is a function of two variables equals to sine of x into y, where x, y both belongs to R. That means jointly they belongs to R2. It is easy to see that this function is continuous at all points in the xy plane. Now, next function let us consider as fxy equals to log of x squared plus y squared, where again x, y both belongs to R, or jointly they belongs to R2. And of course, this function is continuous at all points except at origin, because when both x and y are 0, then log of 0 it would be goes to minus infinity, so it's not really defined. So we can say that the function is continuous at all points except at origin. I am not drawing the graph of this function, but one can try to draw this graph in a three-dimensional space, and it is very interesting to look at the graph and see that this function is continuous at all points but at origin. Next function we consider fxy equals to e to the power or exponential of x plus y divided by x plus y at every point x, y belongs to R. But of course, this function is not defined when x plus y not equals to 0. Again, it is seen that this function is continuous at all points except when x plus y not equals to 0. Now, it is interesting to note that the previous function is not continuous at only one point, that is at point 0, 0. And this function is not continuous at all points satisfying x plus y equals to 0. Now, x plus y equals to 0, we can think that this is the equation of a straight line. So, this function is not continuous at all points on this straight line. That means basically there exists a line on which this function is not continuous. So this is very interesting, that means a function can be discontinuous on a curve. In general, we can show that there may exist another function which is not continuous at a particular curve, not necessarily straight line. Next is a very interesting function f(x(y) equals to xy by x square plus y square if xy jointly not equals to 0 0 and 0 if xy equals to origin or 0 0. Let us see what is the nature of this function with respect to continuity. Now on y axis, y is 0, so we can think that f of xy equals to fx0 equals to 0. Now we can think that this function as a function of x alone is continuous at x equals to 0 because it is a constant function. Similarly, if we put x equals to 0, fxy equals to f of 0 y, which is again 0, that means f as a function of y alone is continuous at y equals to 0 because it is a constant function and of y only. Now this function is continuous at x equals to 0, this function is continuous at y equals to 0. So naturally one can think that the function should be continuous at 0 0, that means at origin. Interestingly, at each point on the line y equals to x, that means except at origin, that means y equals to x. So f xx equals to half for all x equals to y, but it is given that f at 0 0 is 0, that is not equals to half. Hence the function is not continuous at 0 0. So this example is a nice example in the sense that we see that the function is continuous at x equals to 0 as a function of x alone. This function as a function of y alone is continuous at y equals to 0, but when we consider jointly, the function is not continuous at 0 0. So we can think of several other things with respect to continuity of function of several variables, and several very interesting things might occur. Let us now move on to the differentiability with respect to first a scalar function. I am not going to prove any theorem, but just mention certain results, couple of and one or two important theorems. A function f is differentiable or is said to be differentiable at a point A if there exists a linear transformation, say Ta, which is Rn to R, because f is a scalar function, so it maps to R, and a scalar function E of AV such that if we can write this f of a plus v as f of a plus TAV plus norm of v into EAV. Remember, v is a vector, so we have to write norm of v. For or whenever norm of v is less than r for some r greater than 0, and EAV goes to 0 as norm of v goes to 0. So it is clear that the last term is very, we can think of this term as the negligible one. This linear transformation Ta is called the total derivative of f at A. Now, just one small remark that if we define a differentiability, this is basically nothing but the first order Taylor formula for f of a plus v. Now let us just consider one interesting theorem, a very formal one. First consider that f is a differentiable function at A with total derivative Ta. Then the derivative f prime A semicolon y exists for every y belongs to Rn, because it is defined over Rn, and we have Ta equals to f prime A comma y. Now if we look at this thing carefully, it is easy to see that f prime ay is nothing but a linear combination of the components of y. That means if we write y equals to y1 y2 yn prime, that is y is a column vector of n components, y1 y2 yn all are real, then we can write always f prime ay equals to summation k equals to 1 to n dk f of a into yk, where dk f a is nothing but f prime a semicolon ek. Now this f prime a semicolon ek is nothing but the directional derivative with respect to ek, or the partial derivative with respect to ek, where ek is the kth coordinate vector. That means only kth component is 1, all other components are 0. So in this way we can write basically the derivative of a scalar function of several variables. Now let us move on to the differentiability of a vector valued function. Of course we can think that we can easily extend this idea, which is indeed true. Let f is a vector valued function, that means s goes to s to r. It's the mapping from s to rm, where s is a subset of rn. That means it's basically mapping from rn to rm. So Rn means the argument is, or the entries are vector values, it means n dimensional vectors, and f is m by 1 m dimensional functions, and let A be an interior point of S. Then for every y, for any y belongs to Rn, we can define the derivative as f prime a y as f prime a y equals to limit h goes to 0 f of a plus h into y minus f a by h whenever this limit exists. So, you see, if you look at this definition, it clearly reminds us the formal definition of the differentiability of a simple real valued simple function. Now, the derivative f prime a semicolon y is a vector in Rm, that is pretty obvious. Now, we can also write the differentiability of this function, or whether the function is differentiable. You can write this previously, like we said that the function is differentiable at an interior point A if there exists a linear function Ta is Rn to Rm such that f of a plus v equals to f a plus t a v plus norm of v into e a v. Remember, E itself is a vector quantity whenever E of a v goes to 0 as norm of v goes to 0. So, this is more or less exactly the same way we defined differentiability just previously for a scalar function, but function of several variables. Now, so the natural question is, can we extend this, or can we think this thing in terms of first order Taylor formula? Obvious answer is yes. Let us see. So, first order Taylor formula, this one actually holds for all v with norm of v less than r for some r greater than 0. And this linear transformation Ta is nothing but the total derivative of f at like the one that we have just defined. So, basically the idea of simple differentiability of a simple function of real variable can be extended to a scalar function which is based on vector valued variables or vectors, again which can be extended to the vector valued functions of several variables. Now, just to put the same kind of theorem in case of vector valued functions, as if f be differentiable at a with total derivative Ta, then the derivative f prime a y exists for every y belongs to Rn, and we have Ta equals to f prime a semicolon y. And again, if we write y equals to y1 y2 yn prime and f equals to f1 f2 fm prime, because f itself is a vector valued function of dimension m cross 1 or m, we can write Ta as this is called nabla, or the backward difference operator, or f1 a into y, nabla f2 a into y, and so on. This equation can be written using the matrix as Tay equals to dfa into y, where dfa is a matrix, is an m cross n matrix whose nth row as nabla of fk a, and y is a n cross 1 column vector. So, this is just a matrix multiplication of, or matrix, using matrix multiplication we can represent Ta as this dfa into y. Now, let us look at this dfa little more carefully. This matrix dfa is called the Jacobian matrix of f at a, and it is interesting to see that its kjth entry is nothing but the partial derivative dj fk a. So, we can write dfa as a matrix as dfa equals to an m by n matrix. First one is first order different partial derivative of f1 at a, that means d1 f1a, d2 f1a, and dn f1a. That means the first column is nothing but the partial derivatives with respect to each component for the first component function, that is f1, and so on. And this is nothing but, if we write using the partial derivatives, we can write del a1 of f1a and so on. So, this is nothing but, this is very important notion or notation, or important what should I say, a concept or formulation of transforming a set of variables to another set of variables. And this is extremely important in statistics as well as probability theory for multivariate or using multiple variables. A few remarks. Total derivative Ta can also be written as f prime a, just a notation. It is clear that derivative f prime a, which is nothing but Ta, is a linear transformation, which is immediately clear because Ta can be written as d of f a into y using the matrix multiplication. The Jacobian is a matrix representation of this transformation which we have just defined. And lastly, this is nothing but the first order Taylor formula, which we can write formally as f of a plus v equals to f a plus d f a into v plus norm of v, v is a vector, into e a v, e again is a vector, where e a v goes to 0 as norm of v goes to 0. So, here we have defined differentiability of a vector valued function where each component is a function of several variables. So, we have seen that we can easily define a function which is based on vector valued variables, that means based on a vector. And also this function itself can be a vector valued function, that means each component of this function itself is a function of several variables. And we have seen that we can easily extend the concept of limit that we have defined in case of function of a single variable to this new variables or this new function of several variables, as well as we know that how to check whether a function is continuous at a particular point. Now, this point is a vector point, that means it is a point in a n dimensional or higher dimensional vector space. We have also seen that how to consider or how to have some idea about the differentiability of a function that we can also define. And the most importantly, we have shown that we can easily extend one very important theorem in differential calculus, which is known as Taylor's theorem, to the case of vector valued functions or functions of several variables. Although we have only considered the first order form of Taylor's theorem, but this concept can be extended to higher order, to include higher order differentials. So, in a nutshell, we can say that now we have some idea or the basic concept of functions of several variables or the vector valued functions of several variables, along with the notion of limit, continuity and differentiability at a particular point. And also we know the Taylor's theorem, which would be an extremely important tool in calculus or analysis or even in probability theory or in statistics.